Good afternoon, everyone. I'm Kun from UCSD, and currently I'm a 30-year postdoc researcher. And I will present this work on behalf of the authors from my previous research group in Tsinghua University. And the title of the work is Y-Drone, Wi-Fi-based 6DoF tracking for indoor drone flight control. So in recent years, we have witnessed the advent of a wide range of drone-based applications, such as package delivery, security monitoring, and inventory management. So previously, the drones are mainly used in outdoor scenarios, but now the drones began to be applied in indoor applications as well. And research reports show that the indoor drone market will grow by $29 billion by 2027, with an annual growth rate of almost 20%. So the core technique to support drones applications is the drone's 6 degrees of freedom pose tracking. Specifically, during the flight, the drone may change its location with translation and change its orientation with rotation. And these successive movements form a 6 degrees of freedom trace. And the 3D rotation states are collectively referred to as the 6 degrees of freedom pose states. And the 6DoF tracking systems provide a drone with its real-time location and orientation in 3D space, and it enables the self-balancing, path planning, and the speed adjustment of the drones. There are already various existing 6DoF tracking solutions. They work perfectly in outdoor environments, but may fail in more challenging indoor scenarios. So for example, first, the inertial measurement unit is widely adopted for drone flight control. However, the MU-based solutions suffer from severe cumulative drifting errors due to hardware noises and the drone's motor vibration. And second, the GPS-based solutions are widely used in outdoor scenarios, but they cannot be easily applied to the indoor scenarios due to the signal blockage. And third, the vision-based solutions are also very prevalent in recent years. However, these types of solutions are highly dependent on the light and the texture conditions. And finally, the LiDAR-based options may not be good as well, because most LiDAR sensors are designed for automobiles. So they are heavy, bulky, and expensive. So the limitations of existing solutions force us to come up with a new solution for indoor drone tracking. And we propose a Wi-Fi standalone 6DoF tracking system. Compared with existing methods, the Wi-Fi-based solution has following advantages. So first, Wi-Fi-based tracking system can take the access point as a reference, so it is free from cumulative drifting errors. And second, Wi-Fi is agnostic to either illumination changes or visual interferences. And third, the Wi-Fi infrastructures have been widely deployed in the indoor environments, so it makes the Wi-Fi-based solution a ubiquitous solution for indoor device tracking. And last but not least, a Wi-Fi-based solution is considerably lightweight in terms of hardware cost, computation overhead, and payload weight. So here is a summary of the pros and cons of different tracking methods, and we believe that the Wi-Fi-based solution is superior in many aspects. So the next problem is, how can we achieve 6DoF tracking with Wi-Fi? And our key observation is that Wi-Fi signals can be utilized from two different perspectives. So on the one hand, the drone can directly take the access point as reference during its flight and estimate its absolute pose, and we call it exteroceptive tracking. And on the other hand, the drone can also estimate its relative pose to its history poses by tracking the phase change of the Wi-Fi signals. We call it proprioceptive tracking. Therefore, we designed the Y-Drone framework as follows. First, we designed the exteroceptive pulse estimation module, the EPE module, which treats the signal as an exteroceptive measurement. This module takes the AP as an anchor and is free from cumulative drifting errors. And the EPE module estimates the drone's absolute pulse by observing the geometric channel parameters and modeling geometric relationship between the drone and the AP. We also designed the proprioceptive motion tracking module, the PMT module. It leverages the signal as proprioceptive measurements. It infers the drone's relative motion change by tracking the phase change of the received Wi-Fi signals. And finally, the joint optimization and fusion framework takes both the absolute pulse and relative pulse as input. It then optimizes the 6DOF pulse of the drone in real time and reports the optimized translation vector and the rotation metrics. So I'll first introduce the external pulse estimation part. So this EPE module performs mainly two steps. First, the EPE module extracts the direct path signal parameter, including the angle of arrival and the time of flight. With this information, we know both anchor's direction and distance. And on this basis, the EPE module tries to reconstruct the drone's rotation and the location. You may notice that the directional vector n is represented differently as nd and na in the drones and the AP's local reference system. A rotation transformation matrix RAD can be applied to align the two coordinate systems. And this rotation matrix is exactly the drone's 3D rotation state. And the translation vector can be inferred from the time of flight measurement as well. So with these equations, we can solve the 6DOF pulse of the drone, and we can translate the equations to a least square optimization problem and solve it based on matrix decomposition. And therefore, we can get both the absolute rotation and translation in the drone's coordinate system. Then the PMT module leverages the 1D signal phase to track the 6D relative motion of the drone. And this process can be summarized in three major steps. First, from the 1D signal phase change, we can infer the radial distance change of the drone. As shown in the left figure, given a phase change of delta phi, the drone may experience a distance change, relative distance change of delta d. So the drone will be on somewhere on the right plane. But since we only know the 1D phase change, we can only know that the drone is on the right plane, and we don't know its exact location. So to solve this problem, we further extract the phase changes of multi-paths. As shown in the center figure, with 3 paths, we can uniquely determine the location of the receiver as the intersection of 3 planes. And finally, as the drone rotates, different receivers or antennas experience different distance changes. Therefore, we can perform the above 2 steps to all antennas and then infer the drone's overall location and rotation based on all antennas' motion information. So finally, we construct a factor graph to optimize the output of the EPE and the PMT module. And specifically, we factorize the EPE and the PMT module as 2 different types of nodes, each representing their unique tracking model. And we also introduce a constant velocity assumption to the optimization framework. And the 3 error terms are jointly optimized, and a fine-grained 6DOF trajectory without any cumulative drifting errors is reconstructed. So due to time constraints, we only illustrate the basic concept here, and for more mathematical details, please refer to the paper. And we implement Y-drone on an industrial drone as shown in the right figure, and it has 4 commercial network interface cards with a total number of 12 antennas formed into a 3x4 antenna array. And our experiments are conducted in an office building with several typical indoor environments, and various types of 3D trajectories are designed with different rotation angles, post-transfer speeds, and the path lengths. And we use the optic track cameras to get the ground truth, which is at a millimeter level accuracy. And this figure shows the experiment setup and the scenarios. And figure A shows a scenario with satisfactory light and texture conditions. And we also conduct experiments in low light level and textureless conditions as shown in figure B and C. So we compare WiDrone with the state-of-the-art visual and IMU-based solution, WINS Mono, and several Wi-Fi-based tracking solutions. So first, WiDrone achieves comparable overall performance with WINS Mono with an average location tracking accuracy of 26.1 centimeters and an average rotation accuracy of 3.8 degrees. Besides, compared with WINS Mono, WiDrone's location accuracy exceeds it by 60% in low light and textureless sense, and the rotation accuracy exceeds it by 40%. WiDrone's location accuracy is 40% higher than Wi-Fi-based solutions, and its 2D rotation accuracy exceeds others by 50%. We also evaluate the computation overhead of WiDrone. Compared with WINS, the CPU workload of WiDrone reduces by over 40% and it also achieves more than 3 times memory saving. We also analyze the system's robustness. So first, WiDrone works well under various flight speed and still achieves a delightful performance under high speed. And WiDrone is free from cumulative drift. As shown in the top right figure, WiDrone's performance converges to 47 centimeters and 5.1 degrees with a path length over 25 meters. And the bottom left figure also shows that WiDrone can work with any number of AP. Even with one single AP, WiDrone achieves a satisfactory result of 32.2 centimeters and 5.2 degrees accuracy. And the bottom right figure shows that WiDrone's performance highly depends on the number of antennas on the drone. And the performance decreases from 26 centimeters to 102 centimeters when the number of antennas reduces from 12 to 3. And these macro benchmarks show the effectiveness of each module of WiDrone. So first, WiDrone outperforms the EPE-only and the PMT-only versions by 60% and 30% in terms of location and rotation accuracy. And besides, the graph-based joint optimization and fusion module outperforms the classical extended Kalman filter and particle filter by 30% and 20%. And we also analyze the system latency. As shown in the right figure, WiDrone achieves an end-to-end latency of about 52 milliseconds. So here comes the conclusion. In this paper, we propose WiDrone, the first Wi-Fi-based 6DOF device tracking system. And we designed we designed two components and provide a fresh perspective for accurate 6DOF drone tracking with Wi-Fi. And we prototype WiDrone and extensively evaluate its performance. That's all about this talk, and I believe one of the authors is online now and is ready for the questions. So if you have any questions, please feel free to ask him.